This video is all about torque. I've given a definition right here as the product of the force times the lever arm. I've also made a little asterisk here that says it's the perpendicular distance from the line of action. Now, so far this is very vague, so I'm going to draw you a couple pictures. If we took the top view of a door, I actually drew in the door like this, where say here's the hinge, okay, and here's the doorknob, okay. If I twist the knob and then push, then I'm applying a force here that is perpendicular to the surface of the door, okay, or it's perpendicular to the line of action. So this represents the lever arm, which in the torque equation gets symbol R, which makes sense because if this rotated all the way around, right, then that would represent the radius of its rotation, right? We could also think of this in terms of, say, a wrench. So if I had a crescent wrench, right, like this, I know everybody's amazed at my wonderful drawing skills. This would be the lever arm, and then if I push it in this direction, then this would be perpendicular to that line of motion. Okay, so torque has a fairly simple equation. It gets the lowercase Greek letter tau. Okay, since torque is defined as the product of the force times the lever arm, it's just that simple. Lever arm perpendicular to the force. The force does have to be perpendicular, but let's be honest, you don't always push straight on. Sometimes you'd push at an angle. So if I took the same door, okay, and let's say it didn't have a doorknob, okay, but maybe you pushed at this particular angle. Okay, this is where your applied force is. It's only the the perpendicular component, this component here, that really matters. Okay, so oftentimes, if we think about the angle from perpendicular, okay, which would be this particular angle right here. Okay, if we talk about the angle to perpendicular, then this would make this the opposite side of a right triangle. Okay, so this particular equation, and I could also write it with the force where that's perpendicular. Maybe a better way to sum up torque is R F, and then as long as we have the sine of this angle, the side of this angle would give me the component of the force that is perpendicular, or if it was straight on, then the sine of 90 is 1, and we're right back to the actual force. Okay, but this is the issue right here, is where do I draw the angle? You draw the angle from perpendicular. Okay, we want to see how close to perpendicular you are, so that you're solving for technically the part that is perpendicular to the lever arm. Okay, now one thing that also does become a bit confusing is that if we're talking about rotation, you can either rotate something clockwise or counterclockwise. Generally, clockwise rotation is deemed negative, and counterclockwise is deemed positive. And I didn't make those up, that's just the way it is. Okay? So tomorrow in class we'll do a couple examples of how to solve problems with this particular value. But now I'm going to go ahead and move on to equilibrium. Okay? And we've talked about equilibrium in terms of forces, but now we can also talk about equilibrium in terms of torques. So there's a term, static equilibrium, that really has two conditions. the first condition for something to be at static equilibrium is that the sum of all the forces must equal 0. This is oftentimes known as translational equilibrium. The second condition for equilibrium is that the sum of the torques must also equal 0. And this is really referred to as rotational equilibrium. So there's always a classic type of problem where, say we have a seesaw. Okay, and there's a pivot point right here. Okay, if we have a kid that gets on here that, let's say, has, we'll put a person right here, okay, that has a mass of, say, 30 kilograms, okay, and they are at, say, 2.5 meters away, okay, then they would have a force of F of G here that would be at 2.5 meters away. Well, that would be a torque, and in this case it's a counterclockwise torque, which would be a positive torque. Okay, so there's a pretty common question that says, okay, well, if the other person on the other end has a mass of 25 kilograms, then at what distance do they need to sit so that you could balance that particular object, okay, that particular seesaw, if we wanted to just stay there? So this is one of those things where if you had the sum of the torques, well, if we want to be at equilibrium, it has to equal 0. Well, this particular object has a force perpendicular to that lever arm. So that one would be its mass, 30, times 9.8, times its lever arm, 2.5. Okay. Now, if they're going to cancel, then the other one has to be at a certain distance, but it's still its mass, times 9.8, times whatever distance they're at. Okay, because if it's going to be at equilibrium, this has to cancel this. This is a positive rotation, this is a negative rotation. So now really I've got a numerical value with x associated with it, and 0, and you can actually solve for how far from the pivot point that person should sit. Okay, so maybe give that a shot, and then tomorrow in class you can tell me what you get for an answer for how far away they have to sit. Alright, that's all I've got about torque.